All right, open up your book to section 15-3. We're on page 767 in your book. Title of this section is Series and Partial Sums. The objective here is given a series, find a specified partial sum, or find the number of terms if the partial sum is given. Secondly, use sigma notation to write partial sums. And third, given a power of a binomial, expand it as a binomial series. So in the first section of this chapter, we dealt with sequences. And now in this section, we're going to jump into series. All right, so let's start out with a definition of what exactly a series is. And a series is just a sum of a sequence. So given any sequence, if you sum up the terms of that sequence, you have yourself a series. So a series is a sum of a sequence. Notice, by the way, that could be any type of sequence. It could be arithmetic, could be geometric, could be any other type of sequence out there. The other term we need to define as part of the title here is a partial sum. I'm actually going to define here the nth partial sum is usually how we describe this. The nth partial sum is the sum of the first n terms of a series. And it's denoted S sub n. So usually a series, when we're working with it, just like with a sequence, it goes on forever. So we're saying that we're going to take the first n terms, we're going to chop it off at some point and say, okay, let's sum up these first n terms, the first 10 terms, or maybe the first 100 terms, or whatever it might be. And we don't denote that S sub n, where n is the number of terms in our partial sum. We can use what's called sigma notation. That's the Greek letter sigma, uppercase Greek letter sigma there. That's that E-shaped symbol there. But we can use that to represent a partial sum. So S sub n is really just the sum of your terms here, t sub 1, t sub 2, t sub 3, all the way up to t sub n. Right? That's just writing out explicitly what terms you're adding up. But you can then take that and write it as a summation notation or a sigma notation. And we write that as the sum from k equals 1. That's what the number down below means. K equals 1. K is going to be our kind of counter variable. And we're starting it out at 1. The number that you see at the top there, the n, that's your stopping value. So from k equals 1 to n. And then you're just taking each of your terms, t sub k. So when k is 1, that would be t sub 1. When k is 2, it would be t sub 2, and so forth, all the way up to t sub n. So that generates the sequence, and then the sigma notation means you're summing all those things up. So that's our sigma notation we use to represent a series, a partial sum of a series. Now on your calculator, you got a couple of ways that you can do this. Now in terms of what you need to write on your paper, the sigma notation is what you need to write on your paper, or else write out the terms. I don't want to see calculator notation. That doesn't mean anything. That's very specific to your calculator. So mathematically speaking, we don't write down calculator notation. But on your calculator, you have a sum command and you have a sequence command together. That is what a series is. The sequence command generates a sequence for you and creates a list from that. The sum command will then sum up that list. So since a series is defined as a sum of a sequence, that's why we can use these two commands to do that. You'll find these under your list menu. If you press second and then list, you'll find sum and sequence listed under there. You'll have to go over to the sub menus to the right there to find both those. But anyways, S sub n would be the same as the sum of a sequence. And there's 4 things you have to specify for your sequence command. Your t sub k is your actual explicit formula used to generate your terms. You do have to have an explicit formula for this. And then k is your variable that you're using. And then you're starting out at 1 and going to n. So those are the 4 arguments you have to specify. The other way you can do it, if you have the newer operating system on your calculator, there's actually a summation command under your math menu. If you press your math button down there near the bottom, you'll find that there's a summation command. And the partial sum, S sub n, is equal to the sum, that's the sigma notation there. Notice it's the same four parameters that you need for the sequence command. So it's t sub k, then a comma k, comma 1, comma n. So on our calculator, we can generate these really quickly using either one of these techniques. If you've got an older calculator or an older operating system on your calculator, you might have to use the first method. If you've got a newer operating system, a newer calculator, you can probably use the second method, whichever works for you. All right, let's take a look at example 1, and we'll use our calculator here with those examples to help us generate some series here. It says for the series 5 plus 12 plus 21 plus 32 plus 45 and so forth, calculate S sub 100. So again, that's a series that goes on forever, and they're wanting us to calculate a partial sum here, S sub 100. So let's write down the terms in our series. I'm going to go ahead and write this as a sequence to start off with, and then we'll use our calculator to help us calculate the partial sum that we want. So let's write down the first few terms of this. So you have 5, 12, 21, and 32. So just like we worked with in the previous section, you got to figure out what exactly is the pattern here. So you should check to see if it is arithmetic or if it's geometric is the place to start. If it's not one of those two, then you know you got a little bit more work to do. And in this case, it's not going to be either one of those two, so I'm going to just jump into trying to determine the pattern here. If you did look for some of the patterns like we talked about way back in the first semester here at the beginning of the year, you would actually see that this has a common second difference, would be a nice hint that you could use to help you see this pattern. But this turns out to be the product of two numbers. Each of these turn out to be a product of two numbers. 5 is really 1 times 5. 12 is 2 times 6. 21 is 3 times 7. And all of a sudden, you can start to see a nice little pattern emerging here. And in particular, if you want to rewrite this, the 1 is obviously the term number, so I'll leave that as is. But the 5 is really 4 more than the term number. So I'm going to write this as the term number plus 4. And the 6, again, the 2 is the term number, so I'll leave it as is. The 6 is really 2 plus 4, the term number plus 4. And here we've got 3 times 3 plus 4, and so forth. So again, my term number is 1, and these two numbers right there, those two 1s are my term number. The term number is 2, and those 2 that I see there are my term number, and the same with the 3s. Okay, with that, now I can come up with my explicit formula for the sequence. You do need to come up with an explicit formula for the sequence of terms. So our explicit formula here looks like T sub n is equal to, it's my term number, which is n, times my term number plus 4, it looks like is our formula that we came up with over there. Again, if you find out you've got a common second difference, that tells you that you've got a quadratic equation. If you actually multiply this out, you'd end up with n squared plus 4n. And if you grab the first 3 terms from our sequence here and use that and the fact that it's quadratic, you can come up with this quadratic equation here. All right, either way, however you do it, you got to come up with an explicit formula. Now that we've got ourselves an explicit formula, n times n plus 1, let's grab our calculator and use it to find out what the nth partial sum is. Actually, the 100th partial sum is what we're looking for. All right, so on your calculator, let's calculate the partial sums here. I'm going to do it both ways here on my calculator to show you. So if you go to your list menu, under Math, you're going to find that you have a sum command. I'm going to go back to your list menu, and under OPS for operations, you're going to find you have a sequence command, which is number 5. Now again, if you have the newer operating system, it'll bring you up with this little menu to help you enter stuff in. If not, then you'll just be entering this in straight on the home screen there, but you'll see what that looks like here in just a second. Now for my variable, I'm going to go ahead and use k, because that's usually how we write this, but I'm going to show you on your calculator that you don't necessarily have to write it this way, but I'm going to go do it that way first. So my expression is just going to be k times alpha k plus 4. Again, I need an explicit formula to generate the terms of my sequence. Now my variable, of course, is k here. I'm starting out at 1, and I'm trying to find the 100th partial sum, so I'm summing up the first 100 terms. And my step, I'm incrementing k by 1. I'll paste that into my home screen there. So again, there's the little equation that we said you'd have here if you're using your calculator with an older operating system. That's what you type in. Just press enter, and there we go. There technically was supposed to be another parenthesis at the end of that line there, but that's all right. The calculator handled that okay for us. We get 358,550. All right. The other way that you can calculate this, if we go to our math menu now, go all the way down to the bottom, well, near the bottom. There we go. Summation is the one we're looking for, number 0. And now I put in the same 4 arguments that I did up above. But I'm going to change this and put this in terms of x, because x is a little bit easier for me to grab on my calculator. I don't have to press alpha to do that and look around for the k's at, like I was doing. So just realize that you don't have to use k when you type this in. The key is that the variable you indicate in the second argument here, the second parameter, has to be the variable you typed in for the equation. So I've typed my equation in, or my explicit formula in terms of x, so I got to use x here. And I'm starting out at 1, and I'm going up to 100. Now we should see that we generate the exact same value. In fact, let me grab a picture of that. And we'll paste that in right here. All right. So that tells us that S sub 100 turns out to be equal to, it's the sum, by the way, this is the work you need to write on your paper. Don't just write S sub 100. Show me the summation that you've done. But I don't want to see calculator notation. I want to see the actual sigma notation. Sum from k equals 1 to 100 of k times k plus 4. There's what we actually calculated. That's my work. And now I can write down the answer that the calculator crunched for me, which was 358,550. All right, and that's all they asked us to do for that example. So let's take a look at our 2 special series here that we've been working with. That we talked about the arithmetic and geometric sequences. We can also talk about arithmetic and geometric series. So let's start out with the arithmetic series. If we're trying to calculate a partial sum of an arithmetic series, how do we do that? Well, it turns out that there's a nice little formula. You could certainly use the 2 techniques that I just did on my calculator to calculate the sum of any series, as long as I can write an explicit formula for each term, which, of course, if it's arithmetic, we know that. But it turns out there's a nice little formula. It's a little bit faster probably to calculate this. If I want to find the nth partial sum of an arithmetic series, all I got to do is take half of the sum of the first and last term. In other words, you're averaging those two. Half of the first and the last term, and then multiply by the number of terms. So it's 1/2 t sub 1 plus t sub n, and we're multiplying all that by n, the number of terms. Now recall here, when you're working with a arithmetic series, or really an arithmetic sequence we talked about in the previous section, that there's a couple of formulas that we worked with. Over on the left here we have our recursive formulas. T sub 1 equals k, and t sub n is equal to t sub n minus 1 plus d. Over there on your right, we've got our explicit formulas. T sub n is equal to t sub 1 plus n plus d times n minus 1. Or if you don't know the first term, you can write it in terms of any term. T sub n is equal to t sub a plus d times n minus a. All right, let's check this out. Look at example 2. Example 2 there on page 770 in your book says you want to find algebraically the 100th partial sum of the arithmetic series 53 plus 60 plus 67 and so forth. All right, so again, I'm going to start this out the same way here. I like writing this out as a table of data here and listing out what your sequence of terms are, and then trying to figure out what the pattern is. Now, they helped us out on this one because they told us it was arithmetic. Probably the fact that we just talked about an arithmetic series is a big hint too as well, but If they didn't tell you that, then realize you got to go through the same process you've done before to help you figure out what kind of pattern do I see here with these numbers. But clearly you're adding 7 each time, so our common difference is 7. So our explicit formula for T sub n, our explicit formula for T sub n is equal to your first term, which is 53, plus your common difference, which is 7 times n minus 1. All right, so now with that, we can find out what S sub, what do we want, S sub 100? Yeah, they want us to find S sub 100. Actually, one other thing we need to do, to use our formula, we need to know what T sub 100 is equal to, right? I guess I can do that over here. My formula is based on knowing the first term, which I know, and the last term, which I have not calculated yet. So let's do that. So it's 53 plus 7 times 100 minus 1. So it's 53 plus 7 times 99. I'm just going to quick punch that into my calculator. You can do the same. I'm getting 746. You can double check that on your calculator, make sure you're getting the same thing, but that should be T sub 100. Okay, so now, what's our 100th partial sum turn out to be? Well, S sub 100. I'm going to go ahead and write this in sigma notation first, and then we'll grab, we'll evaluate this either on our calculator, or we're actually going to use our formula to do this here in just a second. So this is the sum from k equals 1 to 100 of that equation right there. It's the 53 plus 7 times, it's really k minus 1. Put this in terms of k. That's my partial sum that I'm generating here. This, because of the fact that it's arithmetic, I have another way to calculate this. It's one half of the first term, which is 53, plus the last term, which is 746. I should say the 100th term. There isn't a last term. It goes on forever here. Times the term number, which is 100. So let's grab our calculator and evaluate that. So I've got 1 half of 53 plus the 746, and we're multiplying that by 100. So we get 39,950 should be our 100th partial sum. Again, if you want to check to make sure that's the same value your calculator would spit out there for you, go ahead and do so. I'll quick calculate that. I'll just use my summation to do that. So it's 53 plus 7 times x minus 1. My variable is x, and I'm going from 1 to 100. Again, if we let it crunch there, we should end up with the same result. Same result. Again, you don't need to check both. You don't need to do both calculations, but if you want to verify that you're getting the right result, that's a quick check that you can do there. Just paste this in here. Let's write down that sum there then. 39,950. All right, let's take a look at the other special series that we can deal with, which is the geometric series. When you're working with a geometric series and you want to find out your partial sums, just like we saw with arithmetic, we have a nice little formula that we can use. So what is that formula? Well, here it is. The nth partial sum of a geometric series turns out to be, it's t sub 1, so you have to know the first term. And then it's times this ratio here of 1 minus r to the nth power, where r is your common ratio, all divided by 1 minus r, where again r is your common ratio. Notice in this case I don't need to know the nth term, unlike the arithmetic series. But I have to know my first term and my common ratio. Let's see if we can go through and actually show that that's the case. We're going to prove that here in a second, but just to refresh your memory here of what we know about geometric sequences. On the left there we have our recursive formula. T sub 1 is equal to k. And so T sub n is equal to T sub n minus 1 times r. Over on the right we have the explicit formula. T sub 1 times r to the n minus 1. Or you can do it in terms of any starting point, t sub a times r raised to the n minus a. Look at example 3. Example 3 says if you deposit $100 a month into an account that pays 6% interest per year, compounded monthly, then each deposit earns 0.5% interest per month. For instance, after 4 deposits, the first deposit has earned 3 months of interest. The second one would earn 2 months. Third one has only earned 1 month, and of course the last one hasn't been in there at all, so it doesn't earn any interest yet. Thus the total is, and they give you this total, S of 4 equals that. All right, so the question for part A is, how much will be in the account after 10 years? That is after 120 deposits. Again, I'm going to start out this problem the same way we've started out many of these problems here, which is write yourself a table of this data here. Because we need to find an explicit formula here for the terms, although I think it's pretty obvious what we've got here, but let's go ahead and write these down. So for the first term there, that's 100. The second term of our series here is 100 times 1.05. The third term is the 100 times 1.05 squared. And the fourth term here is 100 times 1.05 cubed. Sorry, it's not 1.05. I've got that wrong. It's not 5% per month. That's really good interest. It's 0.5%. Let me fix that. 1.005. 005. 005. There we go. All right. So the question is, well, how am I going from one term to the next? Again, hopefully that's obvious here, but I'm multiplying this by 1.005. I'm multiplying this by a 1.005, and so forth, right? I'm multiplying by a common ratio. This guy is geometric, is what that tells me. All right, so since it's geometric, I can write my explicit formula for this. I'm going to go ahead and do that, although technically I don't need it for this problem. But I'll go ahead and write my explicit formula for my terms. T sub n is going to be equal to, it's my first term here, which is the 100, times the common ratio, 1.005, raised to the n minus 1. Now with the arithmetic series, I needed this because I needed to find out what that 100th term was. This one, for my partial sum formula, I don't need to know what the 100th term or whatever term number we are calculating here. Well, they want 120 deposit, the 120th term. I don't need to know that term number. But it still is, I think, worth the time here to write it out just so we understand what the explicit formula is. All right, let's write down our partial sum that we're looking for. We're trying to find S sub 120. Now again, in terms of a sigma notation, that's the sum from k equals 1 to 120 of this explicit formula here, 100 times 1.005 raised to the k minus 1. I guess if I'm trying to write the sigma notation, I do have to have that explicit formula. But we have a nice little formula that we just wrote down to help us calculate what this partial sum is equal to. It's the first term times 1 minus my ratio raised to the nth power, which in this case is going to be the 1/20th power, divided by 1 minus my common ratio. All right, let's grab our calculator and see what that gives us here. So we got 100, and we're going to multiply that by 1 minus 1.005 raised to the 1/20th. And we got to divide that by 1 minus r, 1 minus 1.005. And what do we end up with? We end up with $16,387 and some change here. Just grab a picture of that. We'll put that in our slide. All right. So after 120 deposits, we ended up with $16,387. 935, we'll say. Again, make sure you're putting 3 decimal places. Even though it's a dollar amount, I want to see 3 decimal places in your answer there. All right, that was part A. Part B, oh wait, that is not all part A. Part A said, first of all, how much is in the account after 10 years, and then the second part of that is how much of that is interest. So I need to subtract off how much I've actually deposited to figure out how much interest I've earned. So the amount of interest, I take S sub 100, and I'm going to subtract off from that the amount of that I've actually deposited. I made 120 deposits of $100 each. So what is that, $12,000 that I deposited? Well, I guess I can do that without my calculator, right? I can subtract 12,000 from that number, I think. I'd end up with $4,387.935. So it looks like we've made a little over, almost $4,400 in interest over those 120 deposits. All right, take a look at part B now. B says, how long will it take until the total in the account exceeds $50,000? All right, so we want to exceed $50,000. So for part B. So we want to find out when our partial sum, S sub n, is greater than the $50,000 that they're asking about. Now that's really what you're solving there. It is actually trying to find out when the partial sum is bigger than that. So that's what it asks us, when we'll first exceed that. I would suggest you just use the equal sign to solve this and make this an equality versus an inequality and deal with having to mess around with that inequality sign as you go. You'll still work, your work will still be the same, it's just that you won't have to worry about, do I switch this inequality or not, and all that other details that we don't need to worry about. So let's take our partial sum formula, which we've already written down, 100 times 1 minus the 1.005 raised to the nth power, because it's S sub n now that I'm working with, divided by 1 minus 1.005. And I want to find out, when does that actually hit 50,000? Now again, just like we've done here with working with arithmetic and geometric sequences, same is true with series, that you probably aren't going to get a nice integer answer from this solution. Just realize you'll have to round up to the nearest integer when you get done. All right, so let's first get rid of the 100, I guess. If we divide both sides by 100, what's that do? That cancels out a couple of zeros over here, right? So we end up with this is equal to 500. And actually, well, let's do this in a couple steps so we don't screw up this denominator here. 1.005 to the n. That's negative, what, 0.005 when I subtract 1 minus that, negative 0.005. What, dividing by 0.005 is the same as multiplying by a negative 200, right? So I can either think of multiplying both sides by 0.005, the negative 0.005, or I can think of dividing both sides by negative 200. That would be the same thing. I think I'm going to be a little more comfortable here with dividing by a negative 200. That sounds like it end up with a negative 2.5. Again, grab your calculator if you're not sure on that, but that should be what we end up with. Again, we're trying to solve for this value of n, so let's subtract the 1 that we have out front. So I've got a negative 1.005 to the nth is equal to, when I subtract 1, a negative 3.5 is what shows up here. I can multiply both sides by a negative 1. That will get rid of the negatives that I've got there. And now we're solving this with logs to get that exponent. Again, I'm going to use the common log. The log of 1.005 to the nth is equal to the log of 3.5. And again, the whole reason for doing that is because of my property for logs, my power property. This says I can bring that exponent out front right here. And that will help me solve for n. So I've got n log of 1.005 is equal to the log of 3.5. And last step to solve for n is the quotient of these two logs. It's the log of 3.5 over the log of 1.005. Let's grab our calculator and see what we end up with. And again, don't forget, we're going to have to round this answer when we get done, but let's see what this gives us. If we take the log of 3.5 and we divide that by the log of 1.005. We get 251.178 is our number. $251.178 is the value we said we get. And again, you got to round up to the nearest integer, so n is going to be 252. It's going to take 252 deposits before we finally hit our 50,000. So if you're making a deposit each month, if we divide that by 12, that would tell us how many years it's going to take for us to finally hit that amount. That sounds like that's a little over 20 years before we're going to get there. That right there is the end of what they asked us to do, I think, in Part B, right? How long does it take? Yeah, just how many deposits are we going to have to make? All right, and that actually is the end of Part 1 here of Section 15.3.